Welcome back to my course Aspects of Biochemical Engineering. Now we are discussing this kinetics of homogeneous chemical reaction, and last lectures, couple of lectures, we try to concentrate that how to write the mathematical expression for the irreversible chemical reaction, how to write the expression for the reversible chemical reaction, how we write the expression for the chain reaction. And I mentioned that most of the biochemical reaction, their chain reaction and they are reversible in nature. Now, in case of chain reaction, our main emphasis is that how if you look at the profile of the different component present in the reaction mixture, that we find that first component it will keep on decreasing with respect to time, and last component will be keep on increasing with respect to time, but all intermediate compounds they will increase and then decrease. So, our intention was that how to find out that at what time we will get the maximum amount of this intermediate product formation that takes place in the system. So, in the last lectures we try to derive the equation for the different component present in the reaction mixture. Then also we try to discuss this reversible chemical reaction, and I told you at equilibrium condition rate of forward reaction should be equal to rate of backward reaction, and equilibrium constant is equal to concentration of product divided by concentration of substrate. Now, in case of the reversible reaction, that question comes, what should be our strategy to maximize the product formation? Our strategy will be that I try to mention that as soon as the product form, that when the product, if you take out from the system, then what will happen, that more substrate will convert it to a product to maintain the Kc constant. Kc is the equilibrium constant. So, this is how we can increase the product yield of the process, or product concentration of the product yield of the process. Another approach through which we can increase the product formation, because if we add more substrate, because since this is the ratio of concentration of product divided by the concentration of substrate, so if we add more substrate, we will get more product in the process. So, through this approach we can increase the product yield. I can give a typical example that in case of ethanol fermentation process, ethanol is a volatile component. If we applied some vacuum, we can vaporize this out. So, your product concentration decreases. So, more substrate will be converted into product. Now, today I am going to discuss the some numerical problems. 4 numerical problems I am going to discuss in this lecture, and first numerical problem deals with that first order reaction. It is a very simple reaction, A to B, and if you look at the rate, this rate of reaction is given as 0.2 moles per liter per second, where when Ca equal to 1 mole per liter. What is the rate of reaction when Ca equal to 10 mole per liter? So, one condition is there. Suppose we know that if you look at the Ca versus time, if a actual profile is like this. So, in this problem, that maybe this we have at different concentration, you have to find out what is the rate of reaction. So, this is we find at Ca, this is the rate of reaction is this, and Cb, that when the concentration is C10, that this might be 10 and this might be 1. So, at different concentration, what is, so if you look at the equation, it is dCa by dt equal to K into Ca. So, as your concentration increases, your rate of reaction is supposed to be increases. So, that we shall have to find out, and to do this, what we shall have to do that first this is the rate equation that we have, and we put the value. This is RA is 0.2 and this is 1 mole per liter. So here we can calculate the value of K. This is the value of K, we can easily calculate it. This is about 0.2 to the second inverse, and then we put this value in the rate equation. This is 0.2. So our equation now changed to minus RA equal to 0.2 into Ca. Now, so we shall have to find out that at when Ca equal to 10 moles per liter, what is the rate of reaction. We put this is into 10, then it is 2 moles per this is the rate you will get this reaction per liter, then 10 mole per liter, then this will be equal to this 10 mole per liter, then we will have to that increases, that higher substrate, as I told you, as the substrate concentration increases, this value also will be increases. Now, next problem that we have deals with one human system. Human being 75 kg consumes about the 6000 kg of food per day, and assume that food is all glucose, and that the overall reaction is like this. That is the same as when glucose we burn it, the same kind of reaction will take, and if you take in our system, we will get similar type of results, because that 6 moles of carbon dioxide and 6 moles of water. Now, we have heat of reaction is 2816 kilojoules per mole per. So, what we shall have to find out that what is the metabolic rate in terms of moles of oxygen used per cubic meter volume per second. So, this is the things we shall have to find out. Now, how we can do that? Because first we shall have to find out that how much energy we are consuming. We are consuming about 6000 kilojoules. Am I right? Now, if you find out the heat of reaction of glucose is 208.16. This we have. So, if you divide by that, then we can find out for consuming this much of energy how much moles of glucose is required. The moles of glucose that is required, that we can calculate. Now, once you know that moles of glucose required for getting this much of energy, and from this reaction we can find out for 1 mole of glucose you require 6 moles of oxygen. So, once we calculate this, if you multiply by 6, that we will get that how much moles of oxygen that is required in this process. Now, if we divide this with the volume of the man, then we can find out that what is the oxygen used per cubic meter % per second. Let us see how we can solve it. So, our equation is this. Our equation, what is the rate equation we have? Minus RO2 means this is the dNO2. This is the moles of oxygen consumed per cubic meter. This is cubic meter volume of % per second. So, this we shall have to find out. This is our destination. Now, first we shall have to calculate what is the volume of man whose weight is 75 kg. Now, if you want to know the volume of the person or the man, then we shall have to first we should know what is the density of the man. Now, if we know the human contains mostly the water. So, if we assume the density of the human body is close to the water, that is 1000 kg per cubic meter, then if we divide by that, we will get the volume. This is the volume of the person, we can easily calculate. Then if you come here, then I told you that 6000 kg per day we are consuming, the person is consuming energy, and this is the heat content of glucose. Then if we divide by that, we can find out for getting this much of energy how much glucose is required. Then if you multiply it by 6 moles of, because 6 moles of oxygen is required for the consumption of 1 mole of glucose. So, if you multiply that, we will get how much moles of oxygen is required per day. Now, I want to tell you here that here what is the unit that we have, moles of oxygen used per cubic meter per day, am I right? Now, question come how we can convert to per units per seconds. So, this I can show it like this, that suppose we have the data that moles of oxygen per cubic meter per day. How you can convert it, mole oxygen per cubic meter per second, how we can convert? We can convert very easily. How we can convert? This is mole of oxygen cubic meter. Now, this is day, am I right? So, I can write, so here I can write 1 day. 1 day is equal to 24 hours. Then we can write 1 hour is equal to how much? 60 minutes. And then we can write 1 minute, this is multiplied by 60 seconds. So, what basically we shall have to do, we shall have to multiply it by 1 by 24 into 60 to get the value in terms of cubic meter per second. So, this is what we have done in this in this particular place, that you can see that how we have calculated. This has come about 0.002 moles of oxygen used per cubic meter per second. Next problem that we deals with the pasteurization process. Now, as I mentioned that pasteurization is the process through which we can kill the germs. So, mostly the pathogenic organisms. But when we kill the pathogenic organism, obviously some non-pathogenic organism also killed, but the main purpose of pasteurization will kill the pathogens organism. Now, it has been observed that at low temperature it required more time. So, at 63 degrees centigrade it required pasteurization time required is 30 minutes, but if it heated to 74 degrees centigrade only 15 seconds in needed, and for the same results. Find out the activation energy for the sterilization process. Now, here I want to tell you one interesting thing, that this technique, this process we call it HTST technique. HTST technique. HTST means high temperature short time techniques, because we find that if you keep the material at a smaller time, then your destruction of the nutrient, particularly vitamin or amino acid, will be comparatively low as compared to that of if you keep it for longer period of time. The reason is that the deactivation energy requirement for the vitamins and amino acid is much less as compared to that of microbial cells. The microbial cells require more activation energy as compared to that of the amino acid and the vitamins. So, at low temperature it is always detrimental for the quality of the media with respect to vitamin and amino acid. So, if you increase the high temperature, since you are exposed it for a lower period of time, we can maintain the quality of the media in a better way. That is why that we follow in the industry. Now, what I want to discuss here, that how we can find out the activation energy. What is the activation energy? The energy required to have this reaction. What is the energy required? So, to solve this problem, that what I want to tell, that if you look at this rate of reaction, this is dA by dt equal to K into Ca. Am I right? So, if you look at the Ca, that is cancelled. So, your rate constant K, basically it is inversely proportional with time. This is inversely proportional with time. So, now here this is the problem that is given. Now, we know the Arrhenius. What is the Arrhenius equation that we have? Arrhenius equation we have the K equal to A to the power e to the power minus E A by R T. Now, at different temperatures we have different array that K1, suppose this is K1, this is T1, and you can write K2, we have A e to the power E A by R T2. Am I right? Now, this is equal to, I told you this is inversely proportional to this is T1 and this is 1 by T2. Am I right? So, if we write this, then we can, if we solve this, we can get this equation that ln T1 by T2 equal to E A by R 1 by T A. So, in this equation, if we put the value of T A in terms of minutes, then we can easily calculate the value of E A, that is the activation energy required for this process. You can easily find it out. Next problem that we have, that is a liquid A decomposed by the first order kinetics. This is the first order kinetics, and in a batch reaction reactor 50% of A is converted in 5 minutes run. How much longer it will take for 75% conversion? So, this is so we know the fraction that x A is what? X A equal to C A 0 minus C A by C A 0. This is the called fraction. So, if you say this is 50% conversion, then x A will be what? The 0.50. And what if you say 75% conversion, this what we can write, this is equal to 0.75. So, this is exactly what is written there. At 5 minutes is 0.5 and x 2 is 0.75. And what is the rate expression that we have? That minus R A equal to minus d C A by d t into k into this is because this is the follow the first order kinetics. Now, this is the equation that we have. This is from this, if you solve it, we can get this equation ln. So, your ultimate equation is ln C A 0 into k. Now, what is the C A? C A equal to C A 0 into 1 minus x A. Am I right? So, if you put this here, then what you will get? Ln C A 0 into 1 minus x A by C A 0 equal to k into t. So, this will cancel. So, what we will get? Minus ln 1 minus x A divided by 1 equal to k into d. Now, this is what exactly this I told you, this is exactly what you get. This I understand this. Now, at different so since our expression is like this, so at so this is what we have minus, we can have minus ln 1 minus x A k into t. Now, if we use the T1, then it will be x1 x1, and if T2 1 minus x A 2 equal to k into T2. Now, if you take the ratio T2 by T1, how we can write? Minus ln x 2 by 1 minus x A 1. Sorry. Now, this is exactly what we get here, and then we have the expression for T2. What is the expression for T2? T2 is like this, T2 equal to T1 into ln 1 minus this one, and this is another expression that we have. So, so ln 1 minus x1. Now, we know at T1 what is the x A value, and we want to know 75% conversion, what is the time is required. Just we can put the value, we can get the results. So, we find out the time as 10 minutes. So, 75% conversion we require 10 minutes time. This is how we can solve it very easily. So in this particular lecture, what I try to cover that a couple of numerical problems. The first problems I deal with this irreversible reaction, that for the simple first order reaction, that if you know the rate constant at a particular substrate concentration, then we can find out the rate constant at the different concentration that we can find out. Now, second problem that we try to find out, that if in the human system we know that how much energy we are consuming per day, and if we consider that glucose as a source of energy, from that we can easily calculate what is the molecular oxygen consumption that take place by the human beings. And third problem that I deals with the pasteurization process. Pasteurization process basically, I told you, it deals with the killing of pathogenic organism. Now, it has been observed that HTST technique is more useful for this pasteurization process, because effective. Why it is effective? Because you are exposing the food material for smaller time. Though since we know the deactivation energy required for the amino acid and vitamins are very less as compared to that of the microorganism, killing of microorganisms. So, naturally at low temperature it is more detrimental to the quality of the material rather than the killing of organism. So, that is why the high temperature always we require low smaller time for killing the pathogenic organism. So, this problem deals with that, and we try to find out what should be the activation energy required for this particular process. And second and last problem that we also try to find out at a particular time. Suppose in a problem that is given that at 5 minutes time that 50% conversion is there, then if we want to find out that how much conversion is required if you have 75% required for 75 conversion of substrate. Now, this is very important as per chemical and biochemical reaction is concerned, because when you carry out any kind of chemical and biochemical reactions, we always try to we want to know how much is required first, because as you know that as per industry is concerned, that we always look for high conversion efficiency. Because why we look for high conversion efficiency? Because if you have high conversion efficiency, then amount of that substrate remain in the effluent will be comparatively less. And if the amount of organic matter present in the effluent is less, it gives the less load to the effluent treatment process. But if you look at this that other processes now question comes that if you go for the higher conversion or higher percentage of conversion, which is whether it is really economic to the process. So, all these consequence, I think at the end we will discuss in all of my present lecture, this course I shall discuss those issues, that if you increase the conversion efficiency of the process, whether it is really help us for the economic of the process, because this is very important. Because we will find that one way we are reducing the load to the wastewater treatment process, but that is true, but whether it is going to affect the economy of the process. So, that those are the different things we will deal with at the later part of my presentation. Thank you very much.